All right, good morning, everyone. Welcome to this 3D printing virtual tour from the HP headquarters here in California. My name is Carolina Rubio, and I'm going to be your host for today. Let's go into the agenda. This one is going to last for an hour and 50 minutes. We're going to be covering multi-jet fusion technology. We will go over the hardware portfolio that we have, the solutions that we're currently offer, and then we will also go over the step-by-steps of the printing workflow. Then we will move into the materials portfolio, explaining what's the range of materials that we have. And also we will be showing some of the applications that our customers are printing right now using multi-jet fusion. And last but not least, we will have a customer panel. So we have a customer that will join and explain, share with us his experience using the technology, and also taking questions from you guys. So feel free during this whole hour and a half, hour and 50 minutes, to just chat any questions that you have. There's a chat button at the bottom. There's a Q&A button at the bottom. So feel free to just like submit any questions that you have, and then we will take those questions on the fly as we go. Perfect. So let's move into the speakers. We do have two speakers for today. So one is myself. I am also your host. I work as a 3D customer program manager here in Palo Alto in California. And then the other speaker is Wes. Wes, good morning. Wes is based in San Diego in California too.
Good morning, Carolina. Happy to be here today. Looking forward to the presentation. Perfect.
All right. Thank you, Wes. All right. And so we also have, as I mentioned, a customer panel. Paul is going to join us. He's the owner of Runner 3D, and he will be sharing later his experience using multi-jet fusion. Perfect. So let's jump right now into the technology. So what you guys see right here on the screen is what we call the HP Voxel. And a voxel is a 3D representation of a pixel. And basically, this is the basis of our designs in objects. So what's so cool about the voxel is we have what we call voxel control. So we apply the agents. We will see in a minute what agents are, but we apply those agents at the voxel level. And that means that in the future, we will be able to have a part with multiple properties, and multiple properties is something that other technologies cannot do. All right, so let's move into the step-by-step printing process. I was mentioning before that we have agents, and you see it right here. There's two agents, one what we call the fusing agent and the detailing agent. And then we have powder, the powder material. That would be the substrate that we use. To put this very simple, we're going to do a comparison with a traditional printer. In a traditional printer, we do have paper and then we have ink. And here in 3D printing, we have the agents, that would be the ink. And then the powder, the plastic powder would be the paper. Now, the difference between the fusing agent and the detailing agent, the fusing agent is black and absorbs energy. The detailing agent does not absorb any energy and is transparent. Let me take you through the process of the step-by-step process of the printing, the printing workflow. Now, there's here a moment where we're spraying a layer of material in the printable area. And then in the next step, we're going to be applying agents. Now, as you can see right here, we do apply two kinds of agents. We apply detailing agent and fusing agent. The detailing agent goes where we don't want that area to melt. And then the fusing agent goes where we want that area to fuse. Now, in the next step, we're going to apply energy. This is a thermal control process. So we apply energy on top. With the energy, the fusing agent will react to that energy and melt down. And then the detailing agent does not fuse. In fact, it reacts with the energy and evaporates, preventing that area from melting. And the last step is this. What you see is we have fused that layer only where we apply fusing agent. Where we apply detailing agent, that area has not been fused. And then the process repeats again. So we're going to spread another layer of powder on top and then selectively apply this fusing and detailing agent, apply energy for the fusing process to happen. And then the last one is where we have the fused material. And then the rest would be powder that has not been melted. All right, let me take you through this video. This video, it exactly shows this process, but inside the printer. So we're going to be starting by spraying a layer. You know, you see that roller that is moving back to forth and front to back, sorry. And then on the opposite direction, we're going to be moving the carriage. And then with the carriage, we have the spring heads that selectively apply the detailing and fusing agent. Then on top of the carriage, we also have fusing lamps. They're going to raise the temperature to the melting point. And then, as I mentioned earlier, the fusing agent is going to be melting. The detailing agent will not. Then throughout this process, we have heating lamps and thermal camera on the top cover of the printer to control the temperature for the whole job. I will show you this in the lab in a minute. We're going to do a hands-on demo. Let's move now into the hardware portfolio and the end-to-end printing process. So currently, we're offering two solutions, the 4200 and the 5200. The 4200 is a solution that we launched at the very beginning when we started, so 2017, and it's intended for functional prototyping and short mid-volume production. The 5200 is an evolution of the 4200 in terms of like throughput and speed. It goes faster. And basically, the 5200 is intended for high volume productivity. So we do have the ecosystem with the 5200 to be able to rival with traditional manufacturing at the level of accuracy and repeatability of parts. Now, as you guys can see right here, both the 4200 and the 5200 are made of different items that you see. One is a printer. In the middle, you have the container, the trolley. That's what we call the build unit. And then we also have a processing station. And we have designed it that way intentionally. It's designed modular in a modular way, so we maximize the productivity. I will take you through the workflow in a minute in the lab, so you guys will see how it makes sense to have this modular design to maximize the productivity. All right, so let me take you now through the step-by-step of the printing process. Let's see if I can advance the slides. Give me a sec right here. All right, should work now. Perfect. So the end-to-end workflow starts by doing the file preparations. First, we have to decide what job we're going to send to print, how to position the parts in the backhead, and Wes is going to do a brief demo of how to do that with the software that we offer with the solution. Once you have prepared the file, you have created the build, then you send it to the printer. So the next step would be what we call the pre-process. And the pre-process is basically mixing the material and then loading that material into the trolley, into the build unit. Why do we say mixing the material? Because one of the main things of our value proposition is that to maintain the lowest cost per part, we're going to be using reused material from previous jobs. So typically, if we use PA12, polyamide 12, we're going to be talking here of using 80% of reused material from a previous job and then only 20% of fresh material. So when we're saying material mixing is because we're going to decide what is this reusability ratio that we're going to be using. And then once we have decided that, we will load the material into the trolley, into the build unit. Next step, we take that trolley into the printer, and then the printing process can begin. And then after we're done with the printing, there's a post-processing. The post-processing, we're going to cool down the parts, and there's a few options to cool down the parts. You can do fast cooling or you can do natural cooling. And then once the parts are cooled down, then they're ready to unpack. They're ready to be extracted from the trolley. And then the next step would be to clean the parts. We need to make sure that all the powder is brushed off. So we're going to be using different third-party solutions that we have to clean the parts. And last but not least, the secondary process, that's the finishing. Here, this is a total optional process, but there's plenty of options for you guys to use. We can do surface finishing, dyeing, coloring. Wes will also be covering that, so you guys have the big picture of how, you know, what options you have for post-processing. All right, and with this, just a reminder before we start, we're going to take you now into the step-by-step of this end-to-end workflow. Just to make sure that you guys submit any questions that you have into the Q&A chat. So Wes and me will take them on the spot. And with this, I'm going to pass it back to Wes. He's going to take you on that demo.
Great. Thank you, Carolina. So I'm going to go ahead and share my screen now, and we're going to take a look together at HP's free build manager software called Smartstream. So this comes standard with the machine, and it's going to be how we prepare our files for printing. So the first step in this process is simply dragging and dropping our mesh file into the build volume. So mesh file, that could be an STL, OBJ, 3MF. If you know 3D printing, you probably are familiar with those file formats. So we use the same type of file formats. And once you load your part into this build platform, there's a few things that you can do. So you can, move that part around. You can change the angle of this part. So sometimes your print orientation matters because sometimes you want to optimize different things. Maybe it's look and feel, maybe it's dimensional accuracy. For this particular part, we get our most accurate dimensions in the XY direction. We get the best resolution in the XY because that's leveraging our print heads, which have really incredible resolution. So we're actually going to keep this part flat. And what's cool about this part is this is an assembly. So all these gears on here actually move after you print this. And so the unique thing about 3D printing is you can actually print pre-assembled components, which is super interesting. And that is something you couldn't do with traditional manufacturing like injection molding. So once we've selected our orientation, you can move it straight down to the platform. And let's print, maybe a dozen or so of these. So from there, we can hit this duplicate button. We can expand the number of parts we're printing. And next on here, we have this really nifty feature called Autopack, which we specify our part spacing. We'll keep it at 5 millimeters for now. And what this is going to do is it's going to automatically nest all those parts in the build. So you can see on one layer, we have 9 that fit very evenly across. So we'll keep it at 9. If we played around with the orientation and things, we could definitely, I think, fit a little bit more on here. But we're going to keep this for now. And so what's interesting about this technology is if you're printing one part, it would, in a traditional 3D printing technology, it would take, X amount of time. If you're printing 9, it would probably take 9X that amount of time, right? Because you have to trace each one of these parts. With MJF, whether we're printing 1 or 9 next to each other like this, it's going to take the same amount of time. And that's because we use an area-wide printing process versus a point-based printing process. So like you saw in that video Carolina shared earlier, we are able to print a given layer in one single swipe, and that is going to greatly reduce the print time for large amounts of parts. So your print time per layer is always going to be the same. The only thing that's going to influence your total print time is going to be how tall that job is. So this job is pretty short. You can see it's only going to be maybe an hour and a half estimated time. So let's do, one final thing. Let's move these to the center of the platform. And from there, it's going to be as simple as sending to print after printing, or after selecting your material, your print mode, your cooling profile. And a question came up in the Q&A earlier. It said, can you define high volume? When we were talking about the 5200 for high volume production, kind of how do you quantify high volume? Well, with this geometry as an example, let's say we could fit something like 200, 250 of these badge holders in a build. And I think that's actually very doable here. And what's cool is you can take this selection here and you can duplicate that and stack it on top of each other, because with our powder-based printing technology, it's all self-supporting with that powder. So you don't have to print support structures. So you can have parts floating kind of in space like this, and they're going to print. So we can fill this whole bucket up with parts. I think we could get something like 200, 250 in here based on previous experience. And so our print time for a full bucket, and Carolina will talk about this a little bit later, it's about 11.5 hours on the 5200 with our PA12 material. So you're looking at, 24/7 production. You're looking at 2 full builds per day. So about 500 of these parts in a given day. And so that's kind of the range of high volume production that we're talking about. maybe not to the level of injection molding, but definitely a lot higher than the other traditional 3D printing technologies out there. So that was a lot of information, but this is kind of the basics of preparing your files. And now we're going to pass it back to Carolina, and she's going to talk about what we do next in the process.
All right, thank you, Wes. Do you hear me okay?
Yeah, we hear you great.
Perfect. All right, so we're here in the 3D labs. This is the closest that you can see a 3D printing facility. We do have two 5200s running. This one runs with PA12, and we have another one in the back that is right now running PA11. Now, we were mentioning earlier that we have a modular solution. This is a 5200. I want to show you guys and identify the parts that make part of this solution. So this is a printer, this is a build unit, and this is a processing station. And right here, we also have additional accessories that I explain later. So to continue where Wes left it, so he just prepared the file and sent it to the printer. Next step is what we call the pre-process, that is taking this build unit into the processing station to pick what is the reusability ratio that we're gonna use, and then load that mixed material into the trolley, into the build unit. So let me take you through that step. We're going to insert the build unit right here into the processing station. And for you guys to see better, you're gonna come closer with me. Let me take you here. Come closer. Perfect. So right here, I'm gonna open this. So right now the processing station is reading the build unit, and it's going to ask you for two things. The first thing is, what is the reusability ratio that you want to use? I want to show you guys where we have the different materials. I was mentioning earlier, we're using reused material from a previous job, and then also fresh material. The reused material we're storing here. This is the container where we have the reused material. And then the fresh material is right there, right here. So this is a supply. This is a 300 liter, 130 kilograms of PA12, polyamide 12. And this is a supply that, as you see, we have two hoses. These hoses are connected to, if we go over here, you will see, these two hoses are connected to the mixer. So the mixer gets material, is fed from the supply, the fresh material supply, and then also the container where we store the reuse material. And then the mixer is, we're gonna be loading the mixed material into the build unit using this nozzle. This nozzle is connected to the mixer. And so very simple, just put it here, and then we click load. Now, before we even click in, yes.
Yeah, so a really relevant question just came up. I'm sorry to interrupt you, but Michael was asking if there's any issues with contamination of the reused material. So I thought it would be interesting would you be able to open that panel on the bottom right of the machine where it's below the screen?
This one?
Yeah, you can press in. Yeah.
Sure, absolutely.
Let's see if we can see down there. Maybe not. But yeah, you can see there. That's yeah. So that purple container down there in those springs, that's actually a sieve and a filter. And so we, with our processing station, have a really nice process of making sure any sort of contaminants in our reused, reclaimed material is going to be filtered out. And so I thought this would be a good opportunity to kind of show that mechanism and show what steps we've taken to mitigate the potential risk of any sort of contamination with our material.
Yeah, makes sense. Thank you,
Thank you, Carolina.
Perfect. All right. So as I was mentioning, one of the things that the processing station is going to ask is the reuse ratio that you're going to be using. And the other thing is how tall your job is going to be. You don't need to do full jobs all the time. You can decide the height of your job. So people do half jobs. You can do full jobs as well. Just for the record, for this demo, I'm going to be using the full job terminology. So times and productivity is going to be related to a full job here in the 5200. All right, so let's go with the material loading. So we picked 80% of reused material, 20% of fresh material, and then we're going to be doing a full job. Now, because we're doing a full job, that's going to take this process of loading the build unit. It's going to take between 40 to 60 minutes, depending on the material. PA12 will take around 40, 45 minutes. If you're doing half a job, that will take half the time. So we're talking between 20 to 35 minutes to complete the loading process. Next step, now we have loaded the material into the build unit. So we're gonna put the nozzle in parking position. Take these lead, kind of put the lid back. Let me see if I can do this. Perfect. All right. And so the next step would be the printing. So we're going to eject the build unit and then take this build unit into the printer so the printing process can begin. So let me do that. I'm going to, for you guys to see it better, I'm going to extract the build unit right here and then take it into the printer. Perfect. Right here. And now think about it. We have more build units. Actually, we have in the lab, we have right now 3 build units. And what is the beauty of this modular solution that I was mentioning earlier? Whoop. All right, take in. So the beauty of having a modular solution is the fact that the processing station right now is empty, it's free. So we can slide in another build unit that we have right here. And then while this other build unit is printing, this one right here can be loaded with a different material. So this allows you for continuous printing. Do not stop your productivity. That is thanks to this modular solution. All right, I'm gonna take you guys closer to the printer because I wanna show you a few elements that we have here that are really relevant for the printing process. The first one is the top cover. In the video that we just viewed before, we were mentioning that there's like a top cover with heating lamps and a thermal camera. In fact, we have, Wes, correct me if I'm wrong, but I think there's 20 heating lamps here in the top cover, and we also have a thermal camera.
Yep.
Yeah, and these 20 lamps, what the function that they have is just make sure that the temperature is constant throughout the job, throughout the printing process. This thermal camera is going to be taking pictures. If there's any deviation in the temperature, it's going to irradiate. It's going to adjust the irradiation of the heating lamps to make sure that the temperature is the same, is consistent over the whole job. Now, we also have here another element that is the carriage. So if we move over here, I'm going to open this for you, but before I open it, I want to show you the printhead. This is how a printhead looks like for a 3D printer. Now I want to make sure that you guys see this. These are the nozzles, and here the nozzles. This is a technology that we leverage from large format printing. HP has a lot of expertise in traditional printing, and then this comes from the page wide. So these nozzles are going to be selectively applying fusing and detailing agent. So this is how it looks like. So we use 3 of those within the inside of the carriage. So let me open the carriage for you so you guys can see exactly how this looks like. The printheads goes right there, here in the middle. There's 3 printheads. And as you can see, there's a D. I don't know if you can see it from the camera, but let me show you. There's a D, detailing and fusing agent. And now to both sides, we have the fusing models. So these are lamps that are going to be used to fuse the material. And I know there's something really cool about it, Wes, that you want to point out, the fusing lamps.
Yeah, absolutely. So if you're looking at those air ducts there, so those are cooling ducts for our fusing lamps. Those are actually MJF 3D printed parts. And so what's really unique about this, and I think it's a great example of a use of multi-jet fusion, is first of all, this is a geometry that would be very difficult to manufacture with traditional manufacturing. Usually with, these internal hollows like a duct, you would have to do this in 2 different pieces and then join them somehow. This you can do together in one 3D print. It's this unique kind of optimized design to help the flow. And so that's really a great case for 3D printing. And another thing too is we're not making these machines in the quantities of millions every year, right? This is going to be something in the thousands, tens of thousands type of annual production quantities. And so in that range, 3D printing really can be the perfect solution. It can be actually more cost effective than investing in some high-end injection mold tooling. So sometimes 3D printing simply makes sense just because of kind of mid to mid upper range production volumes.
Perfect. Thank you so much, Wes. All right, so here in the carriage, as I mentioned, we have the printheads and we also have the fusing lamps. And then the last element is where the magic happens, is the printing. This is a printable area. So we were mentioning before in the video, I explained you guys how the step-by-step process works, but let me show you here how it would go. We have a slide in the bill unit. The bill unit contains a powder. It has some thermal blankets to keep the temperature, the consistent within the bill unit. And so we also have a mechanism. The bill unit has a mechanism to bring the powder from the bottom up. And then we have the roller right here. The roller is going to spread a layer of powder from the front to the back. Then in the opposite direction with the carriage, we're going to move over. And then with these spring heads, we're going to selectively apply fusing and detailing agent. And remember, we're going to be applying fusing where we want that area to melt. We apply detailing where we don't want that area to melt. The fusing agent is black, the detailing agent is transparent. Now, when the carriage moves over and it's feed both the detailing and fusing agent, to the sides of the carriage, there's two fusing lamps models. These fusing lamps are gonna raise the temperature to the melting point. And so the fusing agent and the detailing agent will be reacting to that energy. The fusing agent will be fused, and then the detailing agent will evaporate, preventing that area from melting. And then the process continues again. So the carriage will go back in position, and then we will be applying another layer of powder front to back with the roller. And then the carriage will move over and then apply selectively fusing and detailing agent, raising the temperature to the melting point with the fusing lamps. And then fusing only where we apply fusing agent. And that's what we call this 3D printing is additive manufacturing. We're adding layers, we're creating the part layer by layer. Now, in terms of timing, normally questions that people have here is like, how much time does it take for the full job to be printed? Remember, we're talking full jobs right here. In the 5200, we have two print modes. There's a fast print mode and there's a balanced print mode. Fast print mode will take around 9 hours. Balanced print mode will take around 11 and a half hours. So that's for a full job. Now, I don't know if we have any questions here in the chat, Wes, for the printing process.
We have one that's maybe more application specific. I don't know if we want to save that for a little bit later.
Let's do that.
Yeah, let's save that one.
All right, perfect. Okay, so we just completed the printing process, and so the next step right now is to do the cooling down. Remember, these parts are at the melting point temperature, so slightly below melting point. So it's 180 degrees Celsius. It's pretty hot. We need to make sure that these parts get cool so we can unpack them. Now, there's two ways of doing that. We can do natural cooling, or we can do fast cooling. That's a feature that the processing station offers. So I want to show you guys the two and how those two will work with the 5200. Before I extract this fill unit, I want to remind you guys that because this is super hot, safety is our #1 priority. The printer will not let you extract the bill unit until you completed a safety cool down. So there's already 30 minutes of cooling down that will happen after the job is printed, just to make sure that you're safe when you extract the bill unit. All right, so let's do that and take it into the processing station so I can show you guys how the fast cooling works. So I'm gonna inject this bill unit right here, and then open the door of the processing station. And now remember what we were talking, this is a modular solution. We're freeing the printer right now, so we can slide in another bill unit that we have with a different job. And so the printer can do continuous printing. We don't want to stop the productivity here. This is a 5200, so this is high productivity solution. So we're gonna push the bill unit right here. We just did that safety cooling down, and then we're gonna take it into the processing station so we can run the fast cooling. We're gonna slide this in. All right, printer is free for another job. And so we take it right here. And before I close this, I wanna show you guys, there's a lead right here that we're gonna be using. Gonna put that on top of the bill unit. Perfect. And then how does the fast cooling works? We're gonna take that lead off, and then we're gonna use this hose. This is a hose that is going to be connected to the bill unit. And what the hose does is it's going to be vacuuming the hot air that circulates inside of the printer, inside of the build unit. So this build unit right here, because it's very hot, there's going to be air, and then the hose, it's going to be vacuuming this hot air that we have. So eventually what happens is there's a fast cooling reaction. So the parts are going to cool down way faster than doing natural cooling. Now, fast cooling typically takes the proportional time that it takes to print the parts. So if it took you 11 hours to print a full job, it's going to take you around 11 hours to do the fast cooling right here. Alternative to the fast cooling is natural cooling. That takes between 24 to 36 hours, depending, on the packing density, depending on the geometry of the parts that you have inside of the bucket. And then for the fast cooling, we have an option. So I mentioned earlier that there's some accessories you guys can see right here. We have these accessories. We turn the camera to our right here. Perfect. So you guys can see some accessories here. This is what we call a natural cooling unit, and this is the forklift. Why do we use this natural cooling? Because we can actually do natural cooling in this unit and then free the build unit to either load another job or print another job. So the way this works is we will place this natural cooling unit on top of our build unit that we have right here. So we have right now a build unit. So we will place a natural cooling unit on top, and then with the forklift, we will place it, put it here on top, and then the processing station will give us an option to transfer the job. The job that we have in the build unit will be transferred into the natural cooling unit. And then with the forklift, we can lift it and then put it away and leave it to cool down. Again, what that means is that this build unit will be free. We can do material loading in this one or take it for printing. So our continuous printing can happen, right? So the customers that use this can have as many natural cooling units as they want, cooling down. So we have all these jobs cooling down while we still have the solution ready to take new jobs. Perfect. I'm going to stop right here. I don't know if you have any questions, Wes.
So we have another one that's a little application specific, but we have one about the fast cooling from Michael. Is there an advantage to part structure to the two cooling methods? He asks, does it influence brittleness at all? So I can address that, Michael. So when we fast cool parts, there might be a slight impact on the mechanical properties of the parts. So we are using semi-crystalline materials in our process, which means that, the level of crystallinity in the parts and therefore kind of the ductility or brittleness is a little bit dependent on the rate at which you cool. I would say fast cooling might promote a little bit better ductility, but I think that the difference would be pretty minimal. Usually what you have to look out for with your fast cooling is the geometry of the part. If it's a long, thin, flat part, it might be a little bit susceptible to warpage because you are going to be inducing a little bit larger thermal gradients on the surface of the parts. That's something to watch out for. But in terms of mechanical properties, I would say the differences, they might exist, but they would be pretty minimal.
Okay.
And then we had one more question from James. Can you explain the mechanics of the layering inside of the build unit? I don't know if you want to take that, Carolina.
Of the layering, what exactly? I'm not sure. The layering, you mean like how the layers work? Yeah,
like how you build layer after layer.
Okay, well, you can take it. I mean, I can
absolutely, absolutely. So the way the build platform works, it's all in that build unit, right? It's self-contained in that build unit. You have powder below, and you have your build platform on top. And so what happens is we have kind of these Archimedes screws on the sides of the build unit that brings the material up to the top. And then the recoater is going to spread that material across the build platform. And then when you're ready for the next layer, that build platform is going to lower. And it's going to allow room for that next layer to get spread on top of it. So we do that over and over and over again. That's kind of the mechanics behind how we do our layers of build.
Yeah. All right. Perfect. And no, if now it's well understood.
Yeah, hopefully that helps.
That helps. Yeah. All right. So next step, we have completed the cooling down of the parts. Now we're ready to unpack the parts. And to unpack the parts, we're going to cue a video to show you how that happens in the processing station. It's going to show me doing that. And I'm going to take you through that process. That is fairly easy. The processing station really gets you through the whole thing. Let's see if we're ready to cue that unpacking video. We also have another option, Wes, if you want to talk about it, that we can talk about it a little later. It's the automatic unpacking station.
Correct. Yeah.
We have another way of doing this. Yeah.
So we're queuing up a video to show the manual unpacking process, but recently HP announced an automatic unpacking station, which is going to be a way to automatically unpack your parts without kind of manual intervention. It's going to be a great option for some of those higher volume production scenarios to reduce the amount of labor time that's spent in the process.
Perfect. So we have right here the video of the manual unpacking. So we're going to run it. This is a processing station. It's going to take you where it's saying unpacking. So it's going to check that everything is ready to do the unpacking. It's going to remind you to use gloves. So safety first, always. You'll see that's the next step. And so we fast forward this video, but basically what we're doing here is with the hose, we're reclaiming the powder. That's going to be powder we're going to be storing for the next job. And so you can see we normally start by the edges, you know, the corners where it's like colder. So always recommend to clean the powder around the build unit and then start in the center with the parts. This is a really big part. And literally with the hose, what you have to do is just reclaim the powder that is loose. You don't have to clean the part thoroughly. We will do that later in the Bead Blaster. So you can see also here at the very end of the processing station, there's some ventilators. And those ventilators are on and they're going to be absorbing any powder that is suspended in the air. And as you can see, as we clean the build unit, we're going to put those parts to the side. As I said, super easy. The platform also, you see that platform that Wes was mentioning, we're just moving the platform up. So we have a better way of just like cleaning everything. And then because this is a big part, I was using here a brush to brush off any powder, but really not necessary if you just want to take the parts to the Bead Blaster after is totally fine. So reclaiming that powder, making sure that we, you know, any powder that is loose, we reuse it for the next job. Now we're going to cue another video. The next video shows the bead blasting, so the cleaning of the parts. Now we have unpacked the parts. We're ready to clean the part completely. And with that, we're going to be using, this is a manual video. It shows a manual process and it's also attended. But Wes, we have ways of doing this in an automatic way, correct?
Correct. There are a lot of kind of automatic bead blasting solutions out there, and the way they operate is usually they have a rotating drum that's going to circulate parts around a stationary blasting nozzle. So this is usually going to be better for smaller parts that are all kind of uniform shape and size. And it's going to be a really nice way to get really even blasting across the surface and do it without manual intervention. But for larger parts like this prosthetic socket, usually a manual bead blasting process is going to be a little bit better.
Perfect. Thank you, Wes. All right, let's come back to the 3 labs. So we have taken you guys through the steps. So remember the file preparation, then the pre-process would load the material into the build unit. Then we take it to the printer. Then once we have the printer, the printing process has been completed, we unpack the parts. We cool them down first, and then we unpack the parts and we're ready to clean them. And so the last step would be the post-processing. So applying some finishing to the parts, that is a total optional step. Wes, I'm gonna pass it back to you so you can guide people through that step.
Awesome. All right, let me pull back up this presentation here. And we will real quickly review again the workflow we just looked at. So again, first part of the process is going to be preparing your files for print. That's going to be packing them all, spacing them, orienting them, selecting your material, your print mode, and sending it to the printer. From there, we're going to make sure our materials are mixed and loaded into our build unit. We're going to print that build unit based on the job we sent. Then we have our cooling that happens after the printing process. That can be done in the processing station with a fast cool. It can be done naturally in the unit, and it can also be done naturally in the natural cooling unit. And then after that, we have our unpacking, which can be done manually in the processing station like we just saw, or there is this option for kind of higher volume production scenarios, maybe when you have multiple unit deployments, to do automatic unpacking with this automatic unpacking station. From there, we need to make sure our parts are clean and free of any excess powder. That's going to happen in our bead blaster, which can be manual or automatic with a rotating drum. And then we give it a quick little air blast rinse to make sure it's free of any of that blast media. And so next up on here is kind of an optional part of the process. And that's going to be our secondary post process. And so things to make the parts prettier or to make them a little bit stronger, things that basically elevate the quality past just coming out of the printer. So let's see here. There were a couple questions that came up, and these are going to get addressed pretty soon here. So let's kind of go through these post processes. And I think the last one that we show here will be a good example pertaining to the first question that was asked by, I don't remember who, I think it was asked in the chat, but it was about if you're able to get a mirror finish. So I'm going to keep working through what we have here. The first post process that I think is one of the more common ones with our technology is going to be dyeing. So here's an example of a gray MJF part. And it's great because you have that black fusing agent inside, you have this white powder surrounding it, and you kind of superpose those two and you get a gray surface. When you dye a part, it's really a nice way to promote good uniform color across the entire surface. You can see here we dye this part black. Different companies like Dye Mansion are enabling different color dyes. A lot of them on this gray MJF surface are going to be kind of the darker colors, but we can't actually dye in color. But again, this is going to be a great, easy, cost-effective way to promote really nice uniform color over the surface of your parts. Another way to do that is going to be with painting. And you can see here in this example, we have different levels of primers and base coats and sanding that's been done ultimately to achieve this really nice high gloss, shiny finish over here. And so with a certain amount of what I call TLC, right, with enough kind of high build primer and sanding, you can get really nice high gloss finishes. But if you're doing something that's maybe, more geared towards high volume production, you don't want to spend manual time sanding, you want to produce a lot of parts quickly, then maybe working with the base kind of surface roughness of the part, applying more of a matte finish, I think is going to usually be a better pairing there. Also, we've seen a lot of success with digitally applied 3D textures, and that might be a conversation for another time. Another post process that's out there that I think is gaining traction very quickly in the market is chemical polishing. So a couple companies, AMT, Dye Mansion, they have vapor polishing technology that put your parts in this chamber, it exposes it to a chemical agent, and that's actually going to slightly melt the surface of the part. It's going to make it much smoother, and it's going to actually make it glossier. It's going to make it darker, more uniform. And this is a post process we're going to see some examples of later on that really helps the part to become kind of this more finished look and feel. Another post process that's one of my favorites is Hydrographics. A lot of different options for patterns that are out here. Here you see a wood grain. And the way this process works is you apply a thin layer of this ink film on the surface of a vat of water, and then you dip your part into that water bath, and it's going to transfer that ink to the surface of your part. And so really limitless types of patterns here. A really interesting way to promote a unique surface and mimic some things that are found in nature, like a wood grain, right? The last on here is electro plating. And so the first question that was asked, was around, can you get this really mirror-like finish with MJF parts? The answer is yes, but not without a lot of manual sanding. So I can tell you this part here was sanded pretty rigorously, I would say on the scale of hours to get it to this level of smoothness before plating. You want it to be perfectly smooth before you do your plating. That's going to take a lot of time. There might be some more automatic processes out there than sanding to get that level of smoothness. And, some of those are like mechanical tumbling or vapor polishing is a good way to promote that type of smoothness, but usually not to the level of kind of hours of manual sanding. So it's possible, but not without some elbow grease. And here on the top is an example of what an electroplated part might look like without that polishing. But you can see here, it is going to, be a post process that not just looks great, but it's going to produce really high strength to weight ratio type parts as well. Awesome. And so next up on here, we have our 3D materials portfolio. First up on here is our high reusability PA12. This is going to be a nylon, and I think it's going to be the best balance of part properties and costs. So it's going to have really good strength, functionality. A question was asked, let's see here. From a materials property standpoint, does this process enable broader industrial applications versus other printing processes? Where does this excel at? And so I would say yes, it does, because we have excellent isotropy. So that's strength in all different directions, whether it be in the XY plane or in Z. With our PA12 material, we have a tensile strength of about 50 megapascals. So compared to a lot of other types of 3D printing technologies out there, and that's in all three directions, right? It's very isotropic. We definitely excel with part strength. Our PA11 is going to be another rigid polymer in our portfolio. It's similar to the PA12, but it's going to have a little bit better ductility, impact properties, a little bit better flexibility. It's going to be tougher. And it's going to be made from renewable sources as well, which is interesting. We also have a glass bead filled nylon 12. This is going to be a little bit stiffer. Our modulus for this is going to be on that 2,900 to 3,000 megapascals type range. And then our last rigid polymer we have available is our polypropylene. This is going to have great chemical resistance, low moisture absorption, is going to have great weldability and other properties like that. Very important for automotive, and we're going to take a look at that a little later on in the application showcase. Last but not least, we have three different TPUs or TPA materials that are going to be our elastomers. They have different availability between the two different platforms, but really unique applications that are being enabled by these materials. All right, so that is our materials portfolio. Now we get to head into one of my favorite parts of this session, which is our application showcase. So Carolina is going to show us some different parts here. We're going to talk about what they are. So a question that came up earlier, I believe it was from Michael, he was talking about the cooling manifold, and it brought up, can we 3D print molds for different things like fiber reinforced composites? So this isn't a fiber reinforced composite, but it is an example of a mold that we do thermoforming over. And so with this application, this is a mold from a company, Nivelipso. They 3D print hundreds of thousands of these unique dental molds every single day. One of our, I say, most successful applications out there is Smile Direct Club. They're printing on the scale of tens of thousands of unique parts every day, and you couldn't do that without 3D printing. It would be very difficult to do without MJF. We saw before just that speed and throughput that we can get with our technology. That's going to be very important for these types of applications where they're 3D printing the molds to do the thermoforming to get your clear dental aligner going straight to the consumer versus having to go through an orthodontist. So yes, Michael, there are a lot of applications out there where we are 3D printing molds, not just the end use parts. Here is a really cool fluid flow application. So this was a part on one of our printers that was a kind of a cooling duct, and it was actually machined before, made up of a bunch of parts. The first step in the process was we consolidated all of those parts into one. So that greatly reduced the cost already, made the part more lightweight. And then we took it a step further. We partnered with Siemens and their CFD software, and we were able to create this topology optimized design that not just reduced part weight and part cost, part materials, but it optimized the flow and increased the flow rate through this part here. And so you can see there's this really unique geometry that you couldn't injection mold, you couldn't tool really. It has to be 3D printed, really unintuitive type design that only this software would be able to generate. Next up on here, we have some really interesting pneumatic grippers. So this is, again, a unique 3D printed design where when you fill that channel with high pressure, it's going to actually cause those grippers to close. So that would be something, again, impossible to manufacture without 3D printing. MJF PA12 is going to provide the fluid tightness and the strength to enable an application like this. Here we have a great example of a functional prototype. So this is from Scorpion Engineering, and they took a side view mirror on an automobile for a prototype they were creating, and they painted it to match the end finish. And you can see just the level of quality that they were able to achieve with this paint coating. So again, I'm assuming they used, kind of a high build primer here. They did maybe a little bit of sanding, but you can get that really nice, Class A type surface quality with our parts. And this, I think, is one of the most beautiful parts that we have on display at our Palo Alto office. And this is from Glaze Prosthetics. They are masters at finishing MJF parts. So this prosthetic arm has been painted and masterfully done. You can see, the level of quality here is far exceeding a lot of other types of technologies we've seen out there, and I think is one of my favorite examples of painting on parts. All right, so that was PA12. Now we're going to take a look at some PA11 applications. And this is, again, one of my favorites here. So these are nasal swabs for COVID testing. And what happened was there was this global supply chain shortage of a lot of different PPE, but also for these critical, swabs for testing. And so HP partnered with Zigzag Design and some other companies to basically take all these 3D printers that were distributed in other sites and start mass producing these nasal swabs in kind of a rescue effort during this global supply chain shortage. And so you can see the flexibility that we're able to achieve there with PA11. And for such a critical application, these get stuck pretty far up a patient's nose. If any sort of part failure happened there and you had breakage, it would be disastrous. So I think it's a true testament to the level of quality that we're able to achieve with our PA11 material and the flexibility we can get. Here we have a helmet from Invent Medical, and it's a good example of dyeing as a post-process, right? But this application, again, these are unique parts that are printed for each patient, and they're used to help reshape cranial deformities in infants. So here, PA11 is going to have a little bit better impact properties than the other materials, and that's why Invent Medical decided to go with this material here. Here's another interesting application from BMW. So this is in their i8 Roadster, I believe, and it is part of their window rail design, I believe, inside their door. So here you see it's an optimized design that's super lightweight, would be hard to manufacture without 3D printing, and that PA11 is going to give it that, strength and that durability that it needs to really perform. Great, now we can get into the TPU. So this is BASF TPU printed on the 5200, and it is from a company. And what's really interesting about TPU and 3D printing together is with that same base material, that same TPU, you can 3D print these different geometries, and it completely changes the performance of the. So here's an example of something that's been designed for impact absorption. And you see with a clever tweak of the design, if you made the unit cells bigger or smaller, or you made the wall thickness thinner or thicker, you can completely tune the characteristics of this part to optimize it for the types of accelerations you're going to be experiencing, the type of impacts you're going to be experiencing. So I think there's a lot of potential lying ahead for 3D printed elastomeric materials. And that's just one example. Another example is something like a bike seat. And these are really nicely finished. I believe this is a flexible coating that's been applied here to these parts. Again, you think of different bike riders, different weights, different geometries. You can custom tailor this design to provide the right support in the right places, the right stiffness in the right places. And with traditional manufacturing, it really might not be possible. So again, great testament to kind of the design flexibility and customizability that 3D printing enables. Again, another opportunity for optimization or personalization. This is a lattice midsole design from Superfeet. Again, by changing the size of those unit cells or the geometry, the thickness of those beams, you can completely change how stiff or how hard the material is. And in this application, instead of impact absorption being kind of what we're designing for, now we're really designing for our rebound. So we want to get, as much springiness out of the midsole as possible. And so with the same base material, just changing the design, we're able to achieve that. So I'm super excited for our elastomeric materials, and I think you're going to be seeing a lot of products out in the market within the next year or so that are going to include this technology. Here is an example from a company, Vestas, and they needed a fixture to hold wind turbine blades and not damage them at all. So this is something that's been custom designed to be, to provide support where it needs to, but also be soft and prevent any damage while it's fixturing that wind turbine blade. And so it's an example of jigs, tooling for specific type geometries. Here we're going back to our rigid polymers. This is polypropylene, and it is another example of a functional prototype. So this is a door defroster. And again, I mentioned how important polypropylene is for the automotive industry. I would say a large majority of the plastics in an automobile are polypropylene. So any type of prototyping that's done in the industry, they want something that can, basically be an analog for their final material, which a lot of times is that PP. We're going to be able to provide that with ours. It is genuine. It is actually chemically polypropylene, and it's going to be a good analog. Here is a gas liquid separator from Oshler, and it's going to be a testament to the chemical resistance and low moisture absorption of our polypropylene material. Both of these have been graphite blasted, which is another kind of post process that allows it to have this nice kind of silvery looking feel and look to it. Here is an example from Xtol that I think really greatly exemplifies welding. So polypropylene, again, going back to automotive, it's very commonly used in a lot of their plastic parts. And because we're using genuine polypropylene, not just, something that's close to the properties of polypropylene, it's chemically compatible. We can not just weld, polypropylene 3D printed parts to other 3D printed polypropylene parts. We can weld 3D printed polypropylene to injection molded polypropylene. And so you think of, like a fascia, a front fascia for, an automobile, a very large part, all the complexity in the little attachment features you can 3D print, you can weld onto that larger injection molded part. So a really interesting opportunity for 3D printing in polypropylene going forward. Here, going back to our elastomers, these are some TPA parts from GoProto. And you can see this is a nice example of our vapor polishing that we mentioned earlier. You can see that almost looks like an injection molded part. So it does a great deal to smooth out that surface, to really seal everything in, and to really make it look like a finished end use part. Excellent. So to recap real quick, we looked at all different types of applications across numerous industries, right? Medical, automotive, consumer goods. MJF is being used across all different industries for all types of different applications, from jigs and fixtures to prototypes, all the way up to high volume production of unique, customized, individualized parts. So this is just the beginning. I'm really excited to be here right now and to see where we might progress in the future. But let me hand it back now to Carolina to take us into the customer panel to talk with someone who's actually had the chance to use this technology firsthand for quite a while.
All right, thank you so much, Wes. So we're going to move into the last part, that is the customer panel. We do have with us today Paul from Forerunner 3D. Paul, good morning.
Good morning.
Thanks so much for joining. So Paul, if you want to take like a few minutes to just tell us about your company and your business.
Sure. So like I said, my name is Paul DeWise. I'm the owner and sales engineer for Forerunner 3D Printing. We originally started out about 11 years ago as a mechanical engineering firm, and really kind of made our name in the automated equipment space. So we're in Western Michigan. Obviously, automotive and office furniture are huge around here. So a lot of that type of assembly equipment. And in 2012, I started pitching my customers, my automation customers that we designed equipment for. I said, why aren't we using 3D printed parts on these machines? And everyone said they'd had bad luck with it. So I went out, realized that the technology wasn't there yet, and just kept my eyes open. And in 2017, when I first saw the MJF machine, I was blown away. It was exactly what I was looking for, and I knew that it would do what I needed to do for my customers. So summer of 2018, we picked up our first MJF machine, and we do, Forerunner does, anything for anyone. If you want prototypes, if you want low volume production, we do all that. But our main focus, and what I'm going to talk about here today, is shop floor automation, jigs and fixtures. There's just a massive amount of opportunity in this space that is really completely untapped. So the two images you see on your screen here, the one on the left is a assembly pallet. So this is for assembling and potting sensors that go into door handles for one of the big three. And basically, when you have your key fob in your pocket, as you walk up, there's a radar in there that senses you walking up in the door handle, and then it pings the Bluetooth and unlocks the car for you without having to get the key fob out of your pocket. All that electronics has to be potted inside of an injection molded housing. And so there's a big potting line where you have about 56 of these trays just running around, and they're filling these customer parts with potting material to weatherproof them. The geometries are really complex, and no one really knew exactly how to design the tray to get it to work when they first built the line. So they wanted a way to rapidly iterate at a lower cost. And so that's what we did. We took and we used CNC machining where it's really good, big flat aluminum parts, things like that. And we used the 3D printing where it's really good, which is the smaller geometrically complex parts. And then obviously loaded them up with a bunch of magnets and springs and purchase parts. And today there's probably 500,000 plus parts a year coming off of this pallet line, all enabled by PA12 on our MJF machine. And it was a massive savings for our customer in both lead time and actual cost. Like a cost for that pallet right there out the door is like $1,200, and to do it in CNC would be double. So that's one of my favorite applications. The other one is this handle core assembly fixture, and we actually have a video here because it's kind of hard to explain. And so what's going on is our customer need to assemble 400 left-hand door handle cores and 400 right-hand handle cores before their automated machines were built that will do this at scale. And this is for a large electric vehicle company. And so there's a spring that has to be assembled inside of this. And to do these by hand, it would just destroy your hands. You need 3 hands to put one of these together, basically. And I haven't met anyone with 3 hands yet. So they needed some tooling, but they needed it fast. Like, this is always the stuff that gets forgot about until like right before launch. And so they called us up and they were like, we have 2 weeks and we need something. So our engineering group jumped on it. We designed up a fixture, and then what you see here is actually the prototype that we built. So the end one actually got built, mounted onto aluminum plate with some extra just ergonomic things in there. But this proved out the design, and we had this done in 4 days. And so Yeah, so this is a really great example of like rapid shop floor tooling. And the one that we ended up building from, we ended up building four, two left hands and two right hands. They ended up putting together thousands of these door handles because their automated machines were late. So they had to start doing production by hand. And I've gotten nothing but good reports back on this. So, so this is a great example of like, end use, factory tooling, like the first pallet, and then rapid tooling that you need to either prove something out or do low volume manufacturing due to timelines.
Okay, thank you so much, Paul. This is so interesting. I have
No
a few
problem.
questions for you. Actually, I know that you're using several materials. You're using PA12 glass beads and TPU Resolve. Is that correct?
Yep, that's correct.
Yeah. So can you tell us about why did you decided to go for this specific materials?
Sure. So PA12, that was our first material. And basically we went with that because that's what the HP recommended we buy. And turned out it's our most popular material. It's a really, really versatile material. We do a lot of wild stuff with it, like machining it after we print it. We do a lot of that. The material properties are great. We do a ton of research. So if anyone's curious, if you go to forerunner3d.com, we have a ton of different testing and different things we've done with it that are unbelievable. Some of the things we're able to pull off with this material. So that's our big runner. Then we added the Lubrizol M95A TPU. And the reason we added that is because in the automation industry, like all the painted parts that you showed, imagine you have to hold on to those while you're doing things like driving clips or drilling holes or gluing or snapping parts together. Well, you don't want to scratch up that nice, beautiful painted finish on your part. So what we do is we use Class A safe nesting. So typically we pour urethane and then we, machine it and then we shove a part in there and it sort of works, but it sucks. And God forbid you need a replacement one because they're like 8 weeks out. What we figured out is the Lubrizol materials are Class A safe. It won't scratch paint. It won't scratch chrome. It won't scratch lenses. We have testing to show all of this, literally videos of me trying to scratch parts with 15,000 cycles of a door handle. And so we print massive amounts of nesting for our machine build customers because it's cheaper than what they can get urethane pours. It holds up better. It's easier to design with. And it's so much faster. So that's why we added the Lubrizol material. And then this spring, we added the glass bead, and mainly because there just aren't a lot of people running glass bead, and there was demand for it, and they needed someone who was competent with MJF. So we added that, and that's mostly low volume production. We see a lot of glass bead being used in those applications where you need some extra stiffness. It has a slightly higher heat deflection temperature too. So we're starting to do some end use tooling for the foundry environments and stuff like that, where you have these higher temperatures that you're dealing with. So yeah, and that's one of the things I'll throw out right now. Like if you're familiar with 3D printing, like the temperature capabilities of the MJF materials is unbelievable. You can go up to, I think it's 365F with nylon 12, which is like unreal. Like we do some crazy stuff with it. We've even powder coated it before. So yeah, it's great material.
All right, so let's talk about your workflow. Can you elaborate a little bit on your experience designing for MJF? I know you talk about the applications, but yeah, basically how was the experience designing, and then how your business changed since you start using MJF?
Yeah. So, we have really, pivoted our engineering group. We still do. Probably 50% of our business is still automated equipment design that has nothing to do with 3D printing. But probably 25% of our business now is designed for additive manufacturing. So just like any process, if you're designing for stamping, if you're designing for injection molding, if you're designing for machining, there are tips and tricks that can help you achieve better quality, better economics, easier parts to make. Additive is no different. Additive in some ways is easier to design for, but also there's a lot of things you can do to really drive better economics of each of those builds and get your price down lower. One of the things that comes to mind is we have a composite sewer lid company that we do a lot of business with, and they have this very low volume product that's a lockable sewer drain cover, and they were going to need to build an injection mold to build this plastic piece that they actually put into the fiberglass of the cover. And they were going to spend all this money, and they only sell maybe 50 of them a year. And so we went in, took their original CAD model and quoted it out, and the price was way too high. And they're like, we can't justify this. And I said, give me a day, let one of my engineers work on it. Let us come back to you. And we went from getting like, I think it was 35 parts per build. We got all the way up to 250 parts per build by making it a snap together design and then coming up with like a Russian nesting doll where they kind of sat inside of each other and you could stack them in the build volume. And we got we knocked 75% off the price per unit. Granted, they had to order more of them, but they don't care. They throw them on the shelf. They use 50 a year. They have no tooling that they have to store. They have no injection molder that they have to work with. They order as they need it. So that was like one of the first projects where we're like, oh man, if you actually design for this, you can do some wild stuff. And so now it's not uncommon for customers to come to us and say, hey, Paul, here's a napkin sketch. Here's a whiteboard sketch. You guys just design the product for us, design the part for us, design the machine for us, and use as much additive as you can. And, there's some customers who want to learn design for additive. There's some customers who just want it done for them. We're happy to help with either, but there's just a lot of, MJF has enabled a lot of low volume production where you can use additive manufacturing to unlock things you could never do before, especially at prices that were never achievable before.
That's awesome. It's awesome to hear, Paul. All right, last question, because we did the hands-on demo in the labs about the machines. How easy it is to use? What's your experience with the machines?
If you take care of the MJF machine will take care of you. It's true. It's true. They're great machines. We have generally one major downtime event a year, and it's just stuff breaks. It happens. But I have a lot of other 3D printing machines too, and I can tell you they spend a lot more time broken than my MJF machines. And I have two 4200s and 4 processing stations, and we run them around the clock, 7 days a week. We run these machines into the ground. And so, if you listen to the field service guys, when they install it, and they are very meticulous, they will teach you everything you need to know about how to take care of this machine. And as long as you stick to that and you don't get lazy, the machines are great. They just run, and they're very problem free. But it's like anything, you have to take care of it. If you think you're just going to buy it, shove it in a corner, and they said I got to clean it every time, but I'm busy today. Yeah, you're at fault in that case. The machine will run if you give it the ability to.
Of course. All right, Paul, we're top of the hour. Thank you so much. It was a pleasure to have you here and to share with us your experience. I really appreciate it. Thank you for your time.
Hey, thank you so much for the opportunity, guys.
Of course. All right, and now we're going to move into the Q&As. We just have 1 minute. I don't know, Wes, if we have something else that we can take on the flight right now.
Yeah.
Questions.
So I typed the answer to some of them, but we can kind of revisit them. So one was talking about sealing or waterproofing, and I actually directed them to Forerunner's website because I love their website. They have all sorts of different testing that they've done with our materials. And so I don't know if Paul might want to jump back on here or not, but I believe you've done a little bit of testing with sealing or waterproofing, correct?
Yeah, yep. So we've experimented with a lot of different post-processing. So the first thing I'll say is these aren't SLS parts. They're sealed. A nylon 12 part coming off the machine it's airtight, it's watertight. Now it's nylon 12, so it does like to absorb water either from the atmosphere or if you get it wet or like coolant or fuels, things like that. It doesn't necessarily leak through the part, but it will absorb into the part, and it can cause a little bit of swelling sometimes. So we've experimented with things like the vapor smoothing process from AMT. That does a really good job of closing off those microscopic pores in the surface. And it definitely helps with water absorption, but you don't have to do that to get a watertight part or an airtight part. The other thing we've experimented with is Cerakote. Don't sleep on Cerakote. It is an amazing coating for MJF parts. It looks great, and it makes a really, really nice surface finish on there. And that can help. Again, we have some defense customers that we do a lot of production parts for, and we dye the parts black, and then we Cerakote the parts black over top of it because they want the sealing effect of the Cerakote. And then if it scratches through the Cerakote, they want the part to be black. So we've had good success with that. So yeah, those would be the two that you can look at for sealing parts.
Awesome. Thank you, Paul. I couldn't say it better myself. That was perfect.
No.
All right, so I think we're top of the hour right now. So if there's any questions that are left to answer, don't worry, guys. We're gonna have those answered offline. Just want to take the time now to appreciate the time of Wes and Paul to be with us. And for you guys, thank you so much for joining. I hope this was useful to you and your business. And if you want to continue the conversation, yes, Paul, go ahead.
Someone in the chat said, can you send me to someone in that group? I'm thinking maybe he's talking about us. Forerunner3d.com. This is the website to go to right here. So is it gonna focus? It's not gonna focus.
Putting it in the chat.
We'll put it in the chat.
Perfect. All right, hit the chat, guys. Sorry for the interruption.
Thanks, Paul. No,
I'm a sales guy. I gotta do it.
Of course. All right. So yeah, I appreciate everyone's time. I hope this was useful, guys, for you and your business. As I said, you guys are going to get a follow-up email. There's a contact there to continue the conversation with a 3D printing representative. You will also get the chance to watch the replay if you're interested. And then with this, yeah, I just want to thank Wes for his time as well and his expertise, of course, and just wishing everyone a very good day. Thank you.